The photograph shows an absence. High inside the atrium of the Hyatt Regency Hotel in Kansas City, openings remain where two suspended walkways once crossed the space. One had connected the second floor. The other had connected the fourth. Both had fallen into the lobby below. The image was preserved among the official records of the investigation. It shows the building after the violence of the collapse had passed, when the structure could be examined as evidence. The empty attachment points, the damaged edges, and the debris below record the final position of a failure whose origins lay much earlier. The Hyatt Regency Kansas City opened in 1980. Its atrium was designed as the hotel's architectural centerpiece, a tall, open lobby crossed by elevated pedestrian walkways. Three bridges linked opposite sides of the atrium at the second, third, and fourth floors. The third-floor bridge was offset from the other two. The second and fourth floor walkways were aligned vertically, one directly above the other. That arrangement created a dramatic interior, but it also placed occupied structures over a public gathering space. Loads from the walkways, and from anyone standing on them, had to travel through steel connections, along hanger rods, and into the roof framing above. The safety of the system depended not simply on whether its major components appeared substantial, but on the exact path taken by those forces at every connection. On Friday, the 17th of July, 1981, the atrium was hosting one of the hotel's regular tea dances. Hundreds of people gathered on the lobby floor. Others stood along the elevated walkways, looking down at the event. Shortly after 7 o'clock that evening, the connections supporting the fourth-floor walkway failed. The upper bridge dropped onto the second-floor walkway beneath it. The two structures then fell together into the crowded lobby. In a few seconds, a social gathering became one of the deadliest structural failures in United States history. The physical sequence was sudden. Understanding why it happened would take investigators backwards through drawings, calculations, fabrication details, construction records, and exchanges between the companies responsible for the building. The wreckage would reveal the immediate mechanism. The documentary record would reveal something broader, a chain in which design intent, altered details, incomplete review, and professional responsibility could not be separated from one another. Before that chain can be followed, the geometry must be understood. Two walkways occupied the same vertical line. Both depended on a suspended support system. And at the fourth-floor bridge, the way those loads were collected and transferred would determine the fate of every person beneath it. The Hyatt Regency was developed by Crown Center Redevelopment Corporation, a subsidiary of Hallmark Cards. The architectural design came from the firm Patty, Berkebile, Nelson, Duncan, and Monroe. Structural engineering was performed by Gillum Colaco International, led on the project by engineer Jack Gillum. The walkway steel was fabricated by Haven Steel Company. That division of labor was normal for a large construction project. The structural engineer produced the design requirements. A fabricator then converted those requirements into detailed shop drawings, showing how individual steel components would be made and assembled. Those drawings required engineering review before fabrication. The review was meant to confirm that the proposed details preserved the structure's intended behavior. The walkways were suspended from the atrium roof by steel hanger rods. In the original design, a single rod was to descend from the roof, pass through the fourth-floor walkway, and continue to the second-floor walkway. Nuts and washers beneath the box beams would support each bridge. That concept was altered during preparation of the shop drawings. Instead of one continuous rod, the fabricated arrangement used two separate sets. The first ran from the roof to the fourth-floor walkway. The second began at that walkway and descended to support the second-floor bridge. The change may sound minor. The walkways remained in the same positions. The visible rods still appeared to connect them to the structure above, but the path taken by the load had changed. With the original continuous rod, the fourth-floor connection carried the fourth-floor walkway. The load of the second-floor walkway traveled through the rod past that connection and continued upward to the roof. With the revised arrangement, the lower rod terminated at the fourth-floor box beam. The fourth-floor connection therefore had to carry not only its own bridge, but also the entire load delivered by the second-floor walkway hanging beneath it. At that point, the demand on the connection was effectively doubled. This was especially important because the rods did not pass through the center of a solid structural member. They passed through welded box beams formed from steel channels. A nut and washer pressed against the beam, transferring the suspended load into its thin steel walls and welded seams. The capacity of that local connection was therefore critical. The revised detail appeared on Haven Steel's shop drawings. Evidence considered during the later proceedings indicated that the change was discussed with the engineering firm and accepted without a complete calculation of its effect. The drawings subsequently received an engineering review stamp. A review stamp did not mean that every dimension and fabrication choice had been independently redesigned. Shop drawing review is generally limited in scope, but the connection at issue was not merely a manufacturing preference. It changed how the weight of one walkway reached the roof, and it increased the force applied at the fourth-floor box beam. The project records did not reveal a complete written calculation verifying the revised connection before construction. That absence became central to the investigation because a straightforward load path check would have exposed the increase. There had already been another structural warning during construction. In October 1979, part of the atrium roof collapsed. The failure was attributed to instability during erection, and the roof was rebuilt. It did not share the same immediate mechanism as the later walkway collapse, but it demonstrated that the atrium structure had experienced a serious failure before the hotel opened. Concerns also arose over deformation in the walkways, yet the completed bridges remained in service. They passed through construction, inspection, and the hotel's opening without the weakness at the fourth-floor connections being identified and corrected. The difficulty was not that the building lacked drawings, calculations, contracts, or professional roles. It was that responsibility was divided across organizations, while the safety of the finished connection depended on those divisions being bridged by effective communication and review. No single drawing could carry responsibility. The engineer's design established the intended load path. The fabricator's shop drawing altered it. The engineer's review allowed the revised arrangement to proceed. Construction then turned that paper detail into steel above an occupied lobby. For more than a year after the hotel opened, the walkways appeared to perform their ordinary function. People crossed them, leaned against their rails, and watched events below. Each successful day concealed the same deficiency. A structure can remain standing while carrying normal loads and still possess dangerously little reserve when the demand increases. On the evening of the tea dance, people gathered on the second and fourth floor bridges. Their weight increased the forces passing through the hangar system. The decisive weakness was concentrated at the fourth floor walkway, where the upper hangar rods ended and the lower rods began. The surviving connection makes that load path visible. A steel hangar rod passes through the box beam. Beneath it, a nut and washer bear against the beam's lower surface. The box beam itself was assembled from two channels welded together along their edges. Under load, the nut pulled upward against the washer. The washer transferred that force into the lower face of the box beam. but the beam walls around the connection were not strong enough to sustain the demand placed upon them. Investigators found that the box beam deformed. Its cross-section changed shape under the concentrated force. The nut and washer then pulled through the steel, separating the connection that held the fourth-floor walkway to the rod above. Once one connection failed, the walkway's load shifted violently into the remaining supports. They could not arrest the movement. The fourth-floor bridge fell onto the second-floor bridge, which was suspended from it. Both then descended into the lobby. The altered hangar arrangement was not the only deficiency revealed by engineering analysis. Investigators concluded that even the connection shown in the original design did not provide the capacity required by the applicable building code. The as-built modification made an already inadequate detail substantially weaker. Tests and calculations by the National Bureau of Standards found that the original connection would have carried only about 60% of the minimum code-required load. Under the revised two-rod configuration, the fourth-floor connection carried roughly twice the load intended at that location, reducing its effective capacity to about 30% of the required minimum. Those figures explain why the disaster cannot be reduced to the crowd simply placing too much weight on a sound structure. The walkways were public spaces intended to carry people. The failure occurred because a critical connection lacked the strength that the design standards required, and because a change that increased its loading was not properly calculated and resolved. The connection also demonstrates why structural engineering depends on more than the apparent size of a beam or rod. Forces follow specific routes. Changing where a rod ends can change which component carries a load. Moving a nut or dividing one hanger into two may transform the behavior of the whole assembly, even when the finished structure looks almost identical. The altered detail was simple enough to draw and manufacture. Its consequences were also simple enough to calculate. Yet the change passed through a process involving designers, fabricators, contractors, and reviewers without anyone completing the verification that would have exposed it. By the night of the collapse, every part of that chain had become fixed in steel. The bridge above carried its own weight, and the people standing upon it. At its underside, the lower rods added the weight of the bridge below. All of those forces converged on a connection whose weakness was hidden inside an otherwise finished hotel. The investigation would now have to determine not only how the steel failed, but how a safety-critical alteration had been accepted without an adequate engineering check. The fallen walkways became a layered mass of concrete and steel. Sections of bridge lay across the lobby floor, surrounded by broken railings, shattered glass, and fragments of the atrium interior. Beneath and between them were the people who had been attending the dance. The collapse killed 114 people. More than 200 others were injured. At the time, it was the deadliest accidental structural failure in the history of the United States. The first response began inside the hotel. Guests, employees, and surviving members of the crowd tried to reach those trapped near the edges of the wreckage. Police officers, firefighters, and medical crews arrived to find a rescue site unlike an ordinary building collapse. The hotel itself remained standing. The danger was concentrated inside its atrium, where two enormous walkway sections had fallen onto a confined, crowded floor. Broken water lines flooded parts of the lobby and threatened people pinned beneath the debris. Electricity in the affected area had to be isolated, leaving rescuers working under emergency lighting. Dust, water, damaged wiring, and unstable structural components complicated every movement. The weight of the wreckage made direct lifting impossible. Rescuers used hydraulic jacks, cutting equipment and heavy machinery to create access. Concrete had to be broken apart carefully because uncontrolled movement could further injure people beneath it. Outside the hotel, cranes were brought into position to help raise larger sections. Medical teams established treatment areas near the atrium. Kansas City hospitals activated emergency procedures as casualties arrived in large numbers. Appeals for blood produced a substantial public response. The operation continued through the night and into the following morning. Rescue work at a collapse site demands speed, but also restraint. Every slab may be supporting another. Every cut can alter the balance of the debris. The same load paths that engineers would later reconstruct on paper had to be judged immediately by crews working around trapped survivors. As the rescue continued, the site was also becoming evidence. The position of the walkway sections, the condition of the hanger rods, and the deformation around the box beam connections could help distinguish between possible causes. Preserving that evidence mattered, but saving life came first. Investigators would have to reconstruct the failure from what remained after the necessary cutting, lifting, and removal. The National Bureau of Standards joined the investigation. Its work combined examination of the wreckage with measurements, material testing, and structural calculations. Investigators compared the surviving components with the design drawings and the fabricator's shop drawings. They traced how each walkway had been intended to hang, how it had actually been assembled, and how the forces changed at the revised connection. The side view of the fallen bridge documented more than damage. It allowed investigators to study the walkway as a system, its concrete deck, steel framing, hanger locations, and the points where the supporting components had separated. Other photographs recorded the box beams, rods, nuts, and washers in close detail. Material failure can sometimes begin with a hidden defect, an unexpected weakness or deterioration that could not readily have been anticipated. The evidence here pointed elsewhere. The decisive connection behaved in a manner that engineering calculations could reproduce. The box beam deformed under the concentrated load. The nut and washer pulled through. The hanger support was lost. Investigators found no need for an extraordinary external event to explain the collapse. The load imposed by people using the walkways was a condition the structure was expected to withstand. The critical question was why the connection supplied to carry that load had so little capacity. The shop drawing change gave part of the answer. Separating the original continuous hanger rod into two sets placed the weight of the lower walkway onto the fourth-floor connection. The investigation then exposed a deeper problem. The original connection itself failed to meet the minimum required capacity. The change doubled the demand at a location that was already inadequate. This distinction mattered. Reversing the fabrication change alone would not have transformed the original detail into a code-compliant connection. The disaster resulted from both an unsafe underlying design and a modification that made the weakness more severe. The documentary trail showed how the revised detail moved through the project. It appeared on drawings. It was submitted for review. It was accepted and fabricated. But investigators found no complete calculation demonstrating that the altered connection could carry the required load. That absence narrowed the gap between physical cause and professional process. The steel had failed in a specific, measurable way. The checking system had failed to detect a specific, calculable deficiency. Responsibility for shop drawings can be misunderstood because they are prepared by a fabricator rather than the structural engineer. A fabricator must produce workable details, but the engineer of record remains responsible for the structural adequacy of the overall design and for reviewing changes that affect it. A review limited to general conformity cannot safely overlook a change to the fundamental load path. The investigation therefore extended beyond the question of who first drew the revised rods. It examined who possessed the authority to approve structural details, who had the information needed to recognize the altered loading, and whether the required professional review had actually occurred. The evidence also challenged the idea that a collapse must be preceded by an obvious final warning. The walkways had remained suspended after construction. Thousands of ordinary crossings had not caused immediate failure. That history did not prove safety. It showed only that the connection had survived the loads previously imposed upon it. On the night of the dance, the bridges carried a larger gathering. As the load increased, the margin between demand and capacity disappeared. The failure was abrupt, but the condition that made it possible had been present since construction. For survivors and families, the engineering explanation could not reverse what happened. Its purpose was to establish the truth with enough precision to assign responsibility and prevent repetition. That required following the chain all the way from the torn steel to the professional decisions behind it. The official findings left little ambiguity about the immediate mechanism. The fourth-floor box beam connection was critically underdesigned. The revised hanger arrangement increased its load. The connection failed, taking the lower walkway with it. What remained contested was not the basic mechanics, but how the duties of design, detailing, review, and construction had been handled. Those questions would move from the wreckage into hearings, legal proceedings, and the institutions governing the engineering profession. At floor level, the scale of the collapse was unmistakable. The walkways that had once crossed the atrium now lay broken across the space beneath them. For investigators, the wreckage preserved the final result of the failed connection. For Kansas City, it marked a loss that extended far beyond the hotel. Civil claims followed on behalf of those killed and injured. The litigation produced substantial settlements, but the legal process could address only compensation and liability. Separate professional proceedings examined whether the engineers responsible for the structure had met the standards required of licensed practitioners. The Missouri Board for Architects, professional engineers and land surveyors found Jack Gillum and project engineer Daniel Duncan guilty of gross negligence, misconduct, and unprofessional conduct. Their Missouri engineering licenses were revoked. The findings focused not simply on the existence of a fabrication change, but on the engineers' responsibility for an inadequate original design and for approving shop drawings containing a safety-critical alteration without verifying the resulting loads. Gillum later accepted responsibility for the engineering failure and spoke publicly about its lessons. His firm ceased practicing structural engineering. The consequences were personal and professional, but they also forced the wider industry to confront a recurring ambiguity: how responsibility is divided when an engineer designs a structure and a fabricator develops its detailed connections. The collapse demonstrated that responsibility cannot safely end at the boundary between design drawings and shop drawings. A review stamp is not a formality when a submitted detail changes the load path. Nor can a structural engineer assume that another participant has checked a connection for which no clear transfer of design responsibility has been established. Professional guidance developed after the disaster placed greater emphasis on defining those duties. Engineers were urged to identify explicitly who was responsible for connection design, to review shop drawings with attention to structural changes, and to document approvals rather than rely on informal exchanges. The lessons reached engineering education as well as practice, where the Hyatt case became a study in load paths, communication, and professional ethics. The technical lesson was precise. A structure must be checked as it will actually be built, not only as it first appeared in a design concept. Every revision affecting the route taken by a load requires calculation. A detail that seems easier to fabricate may place forces somewhere the original analysis did not anticipate. The organizational lesson was equally important. Complex projects depend on many specialists, but shared participation does not mean diluted accountability. If each party assumes that a critical calculation belongs to someone else, an essential task can disappear between contractual boundaries. The Hyatt walkways also showed the danger of treating successful service as proof of adequate design. For more than a year, the bridges remained in place. Their survival under lighter use concealed the shortage of capacity at the connection. Structural safety depends on the required range of foreseeable loads, not merely those a building has happened to experience. Building codes specify minimum loads and safety margins because public structures must tolerate ordinary variations in use. A hotel walkway overlooking a lobby could reasonably be expected to attract groups of people during an event. The crowd on the bridges was not an unforeseeable force imposed on an otherwise adequate structure. It was part of the occupancy the design was required to accommodate. The collapse therefore resisted attempts to describe it as one isolated mistake. The revised rods doubled the demand at the fourth-floor connection, but the original detail was already below the required capacity. The unsafe connection was then carried through detailing, review, fabrication, construction, and occupancy without effective correction. Each stage offered an opportunity to interrupt the chain. A calculation of the original connection could have revealed its weakness. A rigorous review of the revised hangar arrangement could have exposed the doubled load. Clear documentation could have forced the unresolved responsibility into view. None of those safeguards operated successfully. The disaster changed the language of engineering ethics from an abstract duty into a measurable obligation. Protecting public safety meant performing calculations, questioning alterations, recording decisions, and refusing approval when the evidence was incomplete. Professional judgment could not be reduced to a signature or stamp. For the families of the 114 people killed, no procedural reform could balance the loss. Survivors continued to live with physical injuries and the consequences of an evening that had begun as a public dance. The city carried the memory in individual families, emergency services, hospitals, and the many residents who had joined the response. For years, there was no single public memorial naming every person who died. That changed with the creation of the Skywalk Memorial Plaza in Kansas City's Hospital Hill Park. Dedicated in 2015, it commemorates those killed, the survivors, and the rescuers who responded to the collapse. The hotel remained standing and continued operating under later names, while the atrium was reconstructed without the same suspended walkway arrangement. The ordinary life of the building resumed, but the missing bridges became part of the way the disaster was remembered, not as ruins left permanently in place, but as spaces once occupied by structures that should never have failed. The surviving photographs prevent the finished hotel from hiding that history. They show the empty levels, the damaged connection, and the broken walkways on the lobby floor. Together with the drawings and calculations, they preserve a record of cause and consequence. The central failure was small enough to fit within a close photograph, a nut, a washer, and the thin wall of a box beam. But that connection stood at the end of a much larger system of responsibility. Steel failed there because the force exceeded its capacity. The professional system failed because the danger was neither calculated nor stopped. The lasting lesson is not that every accident can be prevented by perfect foresight. It is that this collapse did not require perfect foresight. Its critical weakness could be expressed in an ordinary load calculation. The change that intensified it appeared on a drawing. The required capacity was set by code. What was missing was the disciplined connection between those facts. The Hyatt Regency walkway collapse remains a warning about what engineering responsibility means when the public cannot inspect the calculations for itself. People entering a hotel must be able to trust that every structure above them has been designed, checked, and built to carry the loads it will encounter. That trust is invisible. On the 17th of July, 1981, the structure supporting it was fatally inadequate.